Hello, ladies and gentlemen. I would like first to thank you for attending this webinar, which is about using airborne thermal infrared hyperspectral imaging for mineral mapping. My name is Alexandrine, and I'll be giving you the presentation of today. I've been working at Telops as an application scientist for more or less 3 years now. And if you have any question during the presentation, I invite you to use the question box at the right of your screen. I will try to answer as the presentation goes on. If I miss question, then at the end of the presentation, I will prepare a list of questions from all the attendees, so everybody will benefit from your question. And maybe a week after the presentation, we will send you a recording of the webinar with the Q&A. So here you have the agenda of the presentation. So I will first start with a short introduction about Telops and the product that we offer. Then we will go through some basic notion about infrared remote sensing of minerals, and also about airborne hyperspectral imaging. And then we will demonstrate how this technique can be a powerful tool for mineral mapping with different survey that we've done both in an open pit mine and in urban and rural areas. And then we will conclude. So before starting the presentation, I would like to say a few words about Telops. So Telops is a company that has been founded in 2000, and it is based in Quebec City in Canada. All the production is done here in Quebec. We also have offices in the US and France, and we also benefit from a very large distribution network all over the world. So it's quite easy for you to find information about our products or our services. Over the years, I would say that Telops has developed expertise in manufacturing high-performance cooled infrared camera. So we offer wide range of high-end thermal camera, from broadband to hyperspectral cameras. So let's start with our first product line, the hyperspectral camera that we call the HyperCam. So this kind of camera is kind of system which allow to benefit from thermal imagery, and it also combines benefit from an infrared spectrometer. So for each infrared image in each pixel, you have access to the infrared spectrum, which is very important if you want to do detection, identification, quantification of gases, for example. So this camera allows to get a very, very high spectral resolution. And then we have a multispectral camera. So those cameras are kind of a compromise between broadband and hyperspectral cameras. So multispectral cameras are equipped with an 8-channel filter wheel that is synchronized with the sensor. So this means that you can record while the filter wheel is rotating. So it's providing you a time-resolved multi-channel imaging, so at high speed higher than hyperspectral camera, but lower than high-speed camera, broadband camera, conventional camera, but still that you can get some spectral information, which is not possible here with broadband camera. In terms of broadband camera, we really focus on a high speed. So we have camera that can reach frame rate up to more than 100,000 frames per second. And we also have some high dynamic range camera that allows to follow temperature transition from 0 up to 2500 degrees Celsius. So before going further, it might worth to go through some basic notion about infrared spectroscopy for minerals. So as you probably know, even though you're not a geologist, many minerals can be encountered on Earth. The variety of minerals depend on the chemical element available to form them, but mostly it will be oxygen, silicon, and aluminum. So the different combinations gives here silicates, quartz, pyroxene, and then we have aluminosilicate, such as the old feldspar family here. And then if you add some other atoms, then you obtain olivine, carbonates, serpentine. So all those minerals can be characterized by their infrared signature that is specific to each variety of minerals. So for those who are more familiar with the characterization by remote sensing techniques, you probably know that the visible near infrared and the shortwave infrared sensor are very common and well-established techniques. So in those cases, the signal comes from the overtones and combination of fundamental vibration that occurs in the long wave spectral range that we also call thermal infrared. Unfortunately, though, lots of silicate like quartz are totally featureless in the shortwave and visible near infrared spectral range. So quartz is a mineral that will be for sure encountered. It is pretty common. So it is a problem that the traditional technique cannot detect it. And this limitation also applies to the feldspar and serpentine that are also featureless in the shortwave and in the visible near infrared. The good thing is that all those can be easily detected using a thermal infrared sensor. So the thermal infrared is characterized by the self-emission that is described by the Planck curve here that you can see. So the amount of infrared radiation will vary as a function of wave number, as a function of wavelength, and it will also vary as a function of temperature. So you can notice that there is a shift toward higher wave number, so toward lower wavelength, which means that in the mid-wave spectral range, it's better to have higher temperature to have good signal. And here in the long wave, so usually 8 to 12 microns, you can see that at ambient temperature, you have a lot of signal from the self-emission, because all the target over 0 Kelvin will emit infrared radiation. Also, the thing that you can see here on that curve is that in the case of the shortwave and near infrared visible spectral range, there's no emission. So in those spectral range, it's reflection only, and in the long wave, mid-wave spectral range here, we have both. So both contribution from self-emission and from the reflection. So this is why when we are dealing with thermal infrared imaging, we often refer to the concept of emissivity, which translates the amount of reflection compared to the amount of emission, which is very important for mineral targets. So just a short example, a black body that will absorb all the infrared radiation and re-emit all the infrared radiation has an emissivity value of 1. If we are looking to, let's say, metallic surface, which has a lower emissivity value, close to 0, those kind of material will undergo a lot of reflection instead of emission compared to black body. So this is the same plane curve that we've seen on the previous slide. So it illustrates that there is really no self-emission under ambient condition in the shortwave and in the visible near infrared. So this is the self-emission, in fact, in the thermal infrared that allows us to do airborne or ground-based survey either during the day or during the night. It can be done under different illumination conditions, clear sky or partly cloudy skies. Both will work as the self-emission is not affected by the sun illumination like it is for shortwave or the visible near infrared spectral range. So we can thus carry out surveys all year long, either summer or winter. It's not a problem. So we can do any kind of survey with the thermal infrared sensor. So we are not hearing that much about thermal infrared for mapping, and the reason why is that there is not many commercial solution available on the market. So Telops is one of those who offer one of the few sensors available on the market. So as I mentioned, this sensor is called the Hypercam. This is a high-end scientific instrument that combines benefits from infrared imagery and benefits from an infrared spectrometer. So this instrument is based on Fourier transform spectroscopy that allow to get the spectral dimension. So using Fourier transform spectroscopy, we can get very high spectral resolution that is user selectable, so it can be up to 0.25 wave number. We also benefit from a very good spatial resolution. So here 320 by 256 pixels focal plane array detector. Yeah. So the Hypercam is available in many spectral bands depending of your application. So we have mid-wave, extended, so 3 to 5, 1.5 to 5 micron respectively, mostly used for combustion application, for example. And then we have one sensor that is tuned on the methane absorption for good detection, good sensitivity detection of such gases. And then we have long wave spectral range sensor, which is the one that we have used for the experiment that I will show you today, because in mineral mapping, most of the feature will be in the long wave spectral range, so around 8 to 12 micron. So several accessories are available, such as different optics. So the standard field of view is about roughly 6 by 5 degrees, but we have telescope that will enlarge or narrow down the field of view by factor 4. And then we have polarizer, georeferencing tools, and then we have the Airborne platform, which is of interest for flying with the Hypercam. So the ground-based system can be easily mounted on the Airborne platform, which make the Hypercam very flexible for all kind of survey, either ground-based or airborne survey. The system can be installed in many type of aircraft, so Piper Navajo, Aero Commander 500, for example. So I have mentioned the benefit of using Fourier transform spectroscopy that allow to get a very high spectral resolution, but using this kind of sensor requires some time to acquire a Datacube. So this is why we need to use this kind of stabilization platform here. So our Airborne platform can be used in two different modes. So the first one is the one that we call targeting mode, in which the mission is planned to acquire a number of specific points of interest. So once a point of interest is visible in the image motion compensation mirror angular range, the system tracks the points of interest and record data cubes until the point of interest is out of sight. The second mode is the mapping mode, in which the system follows the mapping flight line and record overlapping cube in order to construct a hyperspectral map, as you can see here. So the acquisition is done frame by frame, as you can see, with a certain overlap, and then we do the image stitching using ortho rectification procedure to get the whole map. So here is just an overview of our software. So here is what we call the mission planners. So here you can determine you can determine different settings. You can customize spectral and spatial resolution depending what you want, which will be mostly determined by your altitude and the speed of the aircraft. So I would say that having the opportunity to change those kind of parameters is a huge benefit compared to a conventional push-broom system in which you are stuck in a single configuration. So here, in order to illustrate how it looks like when we fly with the system, here is an example of a survey above St. Lawrence River here in Quebec City. So you can see that the system is fully automated. It automatically knows when you are in a region of interest. So when you are in the region of interest, it will start recording. And you can see that it also provides you information in real time, such as current speed or altitude. It also knows when you are out of a region of interest, so it will stop the acquisition. And if you prefer, you can use manual mode. So now I would like to talk about the challenge when we do airborne measurement with thermal infrared sensor. Oops, sorry. Here we go. As we have explained earlier, in the thermal infrared, we have two components. So the first one is the reflection from what is surrounding the target. So the sky, environment, it typically refers to the downwelling radiance. The second component is the self-emission of your target, which will be depending inherent to the temperature and the chemical nature of the target. Unfortunately, we have a single measurement for those two components, meaning that those two contributions end up mixed at the sensor level. So now the question is, how can we discriminate the target from what is being reflected? So I'm going to show you how the temperature emissivity issue translates when you do not account for this limitation. So here is a conventional broadband infrared image, so not hyperspectral. So here you can see that we get some crazy temperature measurement below freezing point, and just next to it we have high emissivity object with, let's say, a reasonable temperature. So it's very hard to know what it is, because you don't know if it's cold or if it's reflecting something cold like the sky radiance. The only way to get information about the thermodynamic temperature, let's say the real temperature of the target, or about its chemical nature, is to go through the temperature-emissivity separation. So let's talk about spectral emissivity, just to make sure that everybody is on the same page. So I've mentioned that a black body will absorb all the infrared radiation and re-emit all the infrared radiation as a perfect emissivity value of 1. In addition to that, a black body will have an emissivity that is spectrally flat as a function of wavelength. So it will be a line here at 1. And then we have gray body, which also have a flat emissivity, but an emissivity value that is lower than 1. So here I have an example with the quartz mineral. So it has a very simple infrared signature, but it's excellent from an educational point of view. So you can see that at a lower wave number, or a higher wavelength if you prefer, quartz mostly behave like a black body with high emissivity here. So we could say that this is where the self-emission dominates. At higher wave number, we can see that quartz mostly behave like a reflector with a lower emissivity value. So it means that it will reflect what it sees, and in an airborne survey, what is seen is mostly the sky. So when we are surveying minerals using thermal infrared remote sensing, one thing that we need to never forget is that we are looking at solid, but through atmospheric gases and reflect gases from the skies, as the sky is just a mixture of cold gases. So this means that infrared spectroscopy of gases is also important notion, even for mineral mapping. So here you can see the example that we have. So you can see the quartz in green, and then we have water vapor in blue. So you can clearly see that that absorption feature of gases are pretty sharp compared to the spectral feature of a solid target. So this is, let's say, good for us. So with that, we can take advantage of the high spectral resolution provided by the Telops Hypercam Airborne system in order to unmix the different contribution from mineral, atmosphere, and all that. So here, just to give you an idea of what we get as a measurement with the Hypercam. So if we go back to our quartz airborne survey, we can see that we are looking to quartz. We are having this, which is seen through the atmospheric transmittance through atmospheric gases, but it's also reflecting the sky radiance, which give this typical spectrum here, which is on a brightness temperature scale for a better visualization purpose. So now, if we want to unmix the different contribution, we need to run a temperature emissivity separation algorithm. So we need to solve the radiative transfer model. So here you can see you have the contribution from the mineral, from the target, which has a radiance that depends you have the radiance that will depend from its temperature, and then you have what it is reflect, and all this is seen through the atmospheric gases, and then you have the self-emission from the atmosphere itself. So by doing this TES, we got two outputs. So first is the thermodynamic temperature math, so the real temperature and not apparent temperature, and then we get a spectral emissivity and Datacube, in which we can find information about chemical nature of a target. So now let's go through some example. So the first airborne surveys here, the survey that has been done was carried out in the area of Thetford mines in Canada. So we flew above a Chrysotile open pit mine that is not in operation anymore, but it illustrates well how we can benefit from thermal infrared hyperspectral for chemical imaging. So this whole area here was surveyed. So we have the mining area. Here we have the tailing pound, which is a pound of mining residue. Here we have water pound, and here nearby we have the city of Thetford mine. So the airborne survey was carried out with the long wave sensor. And we were at an altitude of 800 meters, which leads to ground pixel size of 1 meter per pixel. So spectral resolution was set as 6 wave number for a total of 82 spectral band, and 6 flight lines were needed for completing the whole survey. So serpentine is our yellow greenish rocks like this one here, and it results from a serpentinization process which involves hydration of olivine minerals. So here you have the different, let's say, member of the serpentine group. And among them, Chrysotile, which is the mineral of interest for the survey in the mine in the Thetford mines area. So this is an example of what you typically obtain with a broadband sensor, infrared sensor. So we can see here the mining area, tailing pound, and the city here with some vegetation and roads. I would say that the thermal contrast is, in that case, due to apparent temperature. So it is a mix of what it is emitting and reflecting. So the brightness temperature here is affected by both the thermodynamic temperature and spectral emissivity. And also the atmosphere absorbs the infrared radiation, so we have a systematic atmospheric absorption, which will also affect the temperature that we measure with broadband camera. So here you have also the typical measurement associated with different regions here. So we have the calibrated spectral radiance on a brightness temperature scale. So here at the left we have the region A, so in the mining area, and at the right region B, which is the a road. So here we can see that we have, let's say, overall different spectral feature in the two measurements, but still that we have some sharp feature that are similar in the two spectra, and those features comes from the atmospheric absorption and or sky reflection. So we need to unmix this by the temperature emissivity separation algorithm. So this needs to be done for a whole pixel, and here in the two examples you can see that the fit from the TES is pretty good with the measurement that we have done. So once the TES is done, you got the two outputs. So first is the thermodynamic temperature, so this one here, which is the real temperature, not the apparent temperature as we seen on the a few slides ago, where it was the broadband image. So you see here that the temperature is systematically warmer than what was previously obtained with the broadband image, and this is because we got rid of the atmospheric contribution. It's like a systematic offset for all values. So now that we know the emissivity on the ground, we can observe that the temperature are pretty homogeneous, which is what we expect. In fact, we don't expect huge temperature change as we've seen before. The huge contrast that we've seen previously was mainly due to the emissivity contrast of the mineral. So we observe now that the road and rock surface are at similar temperature, while the vegetation is a bit colder, which was also expected. So the second output is the spectral emissivity Datacube, which allows to have information about chemical nature of the target. Unfortunately, we need to unmix the different contribution in the emissivity Datacube because we often look at mixed pixels. So what I want to say about mixed pixel is that the spatial resolution, if you remember, is about 1 square meter per pixel, depending of the altitude, but roughly around 1 square meter. So it means that we will have many different minerals that will contribute to that signal, and it's almost impossible to encounter a square meter in the environment where you will only find one pure crystal. It's always a blend of a bunch of minerals. So here you have the emissivity that were retrieved from the two areas that we have seen before. So region A was in the mining area and region B was on the road. So for the road spectral feature, you can even recognize the quartz feature, if you remember, which correspond to the quartz or sand that is found on the asphalt of the road. So at the left here, at the right, sorry, we have the reference spectra of different minerals, so quartz, calcite, that are pretty common. So all those minerals here have been selected for the linear unmixing. So in that case, we have used reference spectra from commercial libraries such as GHU, GPL, which are free library. But you could also decide to use your own spectra. Also, the Hypercam can be used in an airborne configuration, but it can also be used in a ground-based configuration that allows to record your own spectral signature. So in order to unmix the different contribution within the emissivity component, in order to get the relative abundance map that I will show you in the next slide, we need to do linear unmixing. So here you can see that the different coefficients are corresponds to the relative abundance. So here we have the relative abundance maps overlaid on the broadband image just for clarity purpose. So here we can see for serpentinite and lizardite. So in the case of serpentinite, we can see that it's pretty localized in the mining area and tailing pound, and not much in the city. And similar observation for the lizardite, so very co-localized. For granite and quartz, you can see that granite is a bit everywhere, so in the mine, in the city, which was kind of expected. And then regarding the quartz, we can see that is pretty common, mostly in the city urban area, and this is what I will show you in the next example. But just to finish this one, here we have an overall thematic map, which was derived from the main component at each pixel. So here where we have dunite, for example, it doesn't mean that there is no other minerals, but the main component at this point will be dunite. And serpentine originates from dunite after serpentinization process. So this means that it is where we have dunite, it means that it is a non-altern area. So the whole mining area is full of dunite, lizardite, serpentinite, which are the main rocks from the serpentine group. We can see that the quartz in pink here can be seen everywhere in the city, on the road, and nothing is found in the water pond as expected because it acts as a gray body, meaning that it has an emissivity that is spectrally flat, so no spectral feature. And for vegetation, spectral features are very weak. So where we don't see nothing, it is because there is a flat emissivity or undetermined emissivity, because in that case we were focusing on those minerals. So just a short example about a urban area where we could decide to do chemical mapping. In that case, chemical mapping of quartz, as this is something that we can find everywhere in urban or rural area. So here it's an example of map of Quebec City area, and we can see that many material contain quartz or sand, so all sidewalk, road. As we can detect easily the quartz with the hyperspectral thermal sensor, we could use this kind of sensor in urban area. And here I have a zoom on this industrial area here, and once again you can see that quartz is everywhere. So you can see on the pavement lots of quartz as well. So in rural area, minerals such as quartz is also commonly encountered in soils and sand. So once again, as we can detect this kind of mineral, our sensor could be used for those kind of area. So now that I have shown you what I wanted to do, I hope that it has helped you to understand the benefits from thermal infrared hyperspectral imaging. I think the HyperCam is a pretty flexible system, so you can do either ground-based or airborne survey with the same sensor. It's available in different spectral range depending on your application, mid-wave or the long-wave thermal infrared spectral range. The spectral resolution is user selectable. We have different optics to accommodate different field of view, and our platform can be used in targeting or mapping mode depending of your need during your survey. And as you have seen, the spectral resolution provided by the Hypercam can allow good temperature emissivity separation. And I would say that it is a critical step for being able to retrieve chemical information on the target that you are investigating. So I would say that the Hypercam is a very powerful system. Lots of people prefer to try it before making a purchase decision. So we have a few systems available for rental. So we have the Hypercam methane and also an Hypercam long wave available with the Airborne platform. So this is something that can be possible if you want to try it first. So I would like to finish the presentation by thank you for your for attending this webinar, and your if you have any question, I will stay after the presentation, and I will be pleased to hear about your application. If you want to discuss, do not hesitate to contact us, and we will be more than happy to chat with you. So thank you.